Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello everyone. Today we are going to talk about graph convolutional networks. Could you please tell us more about their use cases in molecular properties modeling?
Graph convolutional networks are a powerful tool for predicting molecular properties. They can be used to predict a wide range of properties, including toxicity, solubility, and reactivity. Graph convolutional networks are particularly well suited for this task because they can capture the complex relationships between atoms in a molecule. Traditional models for predicting molecular properties, like quantitative structure-activity relationships, QSARs, typically represent molecules as a set of features, such as the number of atoms, the types of atoms, and the bond length. However, these features do not capture the spatial relationships between atoms, which can be important for determining a molecule's property. Graph convolutional networks, on the other hand, represent molecules as graphs, where the nodes represent atoms and the edges represent bonds. This allows them to capture the spatial relationships between atoms, which can lead to more accurate prediction. Graph convolutional networks have been shown to be effective for predicting a wide range of molecular properties, including toxicity, solubility, reactivity, binding affinity, and met properties. Graph convolutional networks are a promising tool for predicting molecular properties. They can capture the complex relationships between atoms in a molecule, which can lead to more accurate predictions. As a result, graph convolutional networks are likely to play an increasingly important role in the development of new drugs and materials.
Thank you for that overview. Can you provide a technical explanation of how graph convolutional networks work? How do they incorporate neighbor information and achieve permutation invariance?
Graph convolutional networks, GCNs, are a type of neural network that can be used to predict molecular properties. GCNs work by representing molecules as graphs, where the nodes of the graph represent atoms and the edges of the graph represent bonds between atoms. The GCN then learns to predict the properties of a molecule by learning to identify patterns in the graph. One of the key challenges in using GCNs to predict molecular properties is incorporating information about the local neighborhood of each atom in the molecule. This is important because the properties of an atom are often influenced by the properties of its neighboring atom. GCNs incorporate local neighborhood information by using convolutional filters, which are similar to the filters used in convolutional neural networks, GNN. Convolutional filters are applied to the graph, and the output of the filter is a new graph where each node represents the neighborhood of the corresponding node in the original graph. The GCN then uses the new graph to predict the properties of the molecule. Another challenge in using GCNs to predict molecular properties is achieving permutation invariance. Permutation invariance means that the GCN should make the same prediction for a molecule, regardless of the order of the atoms in the molecule. GCNs achieve permutation invariance by using pooling layers which reduce the size of the graph by combining neighboring nodes. Pooling layers ensure that the GCN does not overfit to the specific order of the atoms in the molecule.
That is very interesting. How are graph convolutional networks implemented in practice? Could you walk us through the process of creating graphs from chemical structures, building the network architecture, and training the network on a dataset of molecules with known properties?
Graph convolutional networks, GCNs, are a type of deep learning model that is specifically designed to work with graph data. Graphs are a way of representing data that is made up of nodes and edges, and they are often used to represent things like molecules, social networks, and transportation networks. To implement a GCN, we first need to create a graph study of our data. In the case of molecules, we can represent each atom as a node and each bond as an edge. Once we have created a graph study of our data, we can then build a GCN model. A GCN model is typically made up of several layers, each of which consists of a convolutional operation and a pooling operation. The convolutional operation applies a filter to each node in the graph, and the pooling operation reduces the number of nodes in the graph type. The output of the last layer of the GCN model is a vector that represents the entire graph. Once we have built a GCN model, We can then train it on a dataset of molecules with known properties. The model will learn to predict the properties of new molecules based on their graph residency. GCNs have been shown to be very effective for a variety of tasks in chemistry, including predicting molecular properties, generating new molecules, and classifying molecules. They are a powerful tool for understanding and manipulating chemical data.
Thank you for explaining the implementation of graph convolutional networks. How do GCNs address the challenges of predicting molecular properties, such as the lack of continuous inputs and permutation invariance?
Graph convolutional networks, GCNs, are a type of deep learning model that can be used to predict the properties of molecules. They are able to do this by learning the relationships between the atoms in a molecule and how these relationships affect the molecule's properties. One of the challenges in using GCNs to predict molecular properties is the lack of continuous input data. Unlike images or text, which can be represented as a grid of pixels or a sequence of words, molecules are represented as graphs, which are made up of nodes, atoms, and edges, bonds. This makes it difficult to apply traditional deep learning techniques to molecules. Another challenge is that GCNs must be permutation invariant. This means that the order of the atoms in a molecule should not affect the model's predictions. This is important because the atoms in a molecule can be arranged in many different ways, and we want the model to be able to make accurate predictions regardless of the arrangement of the atom. To address these challenges, GCNs use a number of different techniques. One common technique is to use a message passing scheme. In this scheme, each node in the graph sends a message to its neighbors, and each neighbor updates its own state based on the messages it received. This process is repeated until all of the nodes in the graph have updated their state. Another common technique is to use a pooling operation. Pooling operations reduce the number of nodes in the graph by combining them into larger groups. This helps to make the model more robust to noise and to reduce the computational cost of training. GCNs have been shown to be very effective for predicting a wide range of molecular properties, including toxicity, solubility, and reactivity. They are also being used to develop new drugs and materials.
Could you provide more details about the evaluation metrics used to assess the performance of graph convolutional networks, GCNs, in predicting molecular properties?
The performance of the model was evaluated using the following metrics. Mean absolute error, MA. This metric measures the average absolute difference between the predicted and actual value. A lower MA indicates a better model performance. Root mean squared error, RMC. This metric measures the square root of the average squared difference between the predicted and actual values. A lower RMEC indicates a better model performance. R squared, R2. This metric measures the proportion of variance in the actual values that is explained by the predicted value. A higher R2 indicates a better model performance. Concordance correlation coefficient, CCC. This metric measures the agreement between the predicted and actual values, taking into account both the correlation and the agreement of the mean values. A higher CCC indicates a better model performance.
How does the performance of graph convolutional networks, GCNs, compare to other machine learning methods for predicting molecular properties, such as random forests or support vector machines?
Graph convolutional networks have shown to outperform other machine learning methods, such as random forests or support vector machines, in predicting molecular property. This is because graph convolutional networks are able to capture the complex relationships between atoms and bonds in molecules, which is essential for accurately predicting molecular properties.